In today's lesson, I'd like to introduce the idea of the complex exponential. This is something that will be continuously used not only as an actual function, but as a means to actually represent complex functions in the form of their Taylor series. Okay, so what we want to do in today's video is really explore the motivation behind the complex exponential and its profound relationship with the sine and cosine functions, of course deriving the Euler identity, following which we will spend the video after discussing the impacts that it has on the complex algebra that we've been discussing previously. So let's take the time now to discuss the complex exponential's motivation in depth. So the motivation here is to retain the properties of the general exponentials that you talk about in elementary functions. This, of course, means that the exponential of two products, or of the product of two exponentials, so e to the a times e to the b, is equal to e to the a plus b. Of course, you can do the same for the quotient. If you have e to the a over e to the b, then you can do e to the a minus b. And finally, if I have e to the, if I have e to the a all raised to the bth power, then that's equal to e to the a times b. Okay, so those are some properties that we have, but essentially what we want to do is we want to give that over to the complex numbers. So of course we represent a complex number with the number z, which is x plus iy. So if I have e to the z, then I have e to the x plus iy, which is e to the x times e to the iy. Furthermore, just from a calculus standpoint, I want to retain the special nature of the exponential function such that its derivative of it is itself. So if I have the derivative of e to the z, I still want to get e to the z out of it. Okay, now this is where we get the first problem, or I guess hint, that something deeper is going on here. If I want to differentiate e to the z, I can differentiate e to the x fairly easily because that is a real number and I can differentiate a real number. The derivative of e to the x is e to the x. However, the complex part of the exponential is e to the iy. So if I want to differentiate e to the iy, then I will pull out I as a constant and use the chain rule, and of course that will provide the derivative of I times e to the iy. That's fine. Of course, we're kind of shoving a lot of stuff under the rug right now. Taking derivatives of a complex function is not something we'll do until a couple units later. But anyways, we'll just treat I as a constant for now that can be multiplied with itself. Anyways, if I want to take the second derivative of e to the iy, so I'm taking the derivative of I times e to the iy, I pull the I out again, but of course I already have an I sitting down there. So I get I times I, which is negative 1. So what I get is that the second derivative of e to the iy is equal to negative e to the iy. Now, why is this so special? Well, because this creates a solution to a very interesting differential equation. We see that the second derivative of a function is equal to the negative of its original function. The only place we see that in the real calculus is in trigonometric functions. Now, this is where the light bulb should really be going off because we're going to make a couple of extremely profound connections today. So this, of course, provides the reasoning and motivation for the Euler identity. Okay, so let's derive the Euler identity through the means of a differential equation solution. So we know that there is some function, which we'll call g, such that g of y is equal to e to the iy. And we already saw last slide that this function satisfies the differential equation that the second derivative of g is equal to negative g. Now, of course, in physics or in single variable calculus, you'll know that this is the solution to the simple harmonic oscillator. So we know that the solution is a linear combination of sine functions and cosine functions. So we let g of y equal a cosine of y plus b sine of y. Of course, this is a solution to the differential equation above as well. So now we have two solutions to the differential equation. We have the solution e to the iy. We also have the solution a cosine y plus b sine of y. So what we're going to do is we're going to set them equal to each other, and then we're going to find the boundary conditions to find our amplitudes a and b. So we have the following equation. E to the iy is equal to a cosine y plus b sine of y. This should already be incredibly profound. What we're doing here is we are looking at the multiplication system that the complex numbers reside in. If this is the complex plane, I start off with the number if I multiply I once, if I take I to the 0th power, I get 0, okay? Or I get 1. I to the 0, anything to the 0th power is 1. So I start there. If I multiply I again, I to the 1st power is I. I to the 2nd power is negative 1. I to the 3rd power is negative I to the 4th power is 1 again. So what we see is as we keep multiplying by I, we end up rotating, right? Not just alternating like we would when we keep multiplying negative 1 by itself, but we actually rotate around in the complex plane, around a unit circle. We are doing rotations around the unit circle as we multiply by I. So this should be where we kind of see the idea of rotation coming in. Anyways, we have this differential equation, and we want to plug in the boundary conditions. So we'll do this for the derivative and for the general function. So e to the I times 0 is equal to a cosine of 0 plus b times sine of 0. And then we can use the derivative as well of e to the iy and plug in 0. So we get I times e to the I 0 is equal to negative a sine 0 plus b cosine 0. Now we can use this as a linear system of equations. And then, of course, two of the terms will cancel out because the sine of 0 is 0. And we get expressions for a and b, such that a is equal to 1 and b is equal to I. Thus we have derived Euler's identity, which says that e to the iy is equal to cosine of y plus I times sine of y. Of course, this also has the very important property that if I plug in pi for this, e to the I pi is going to be equal, I believe, to, so if we plug in pi, cosine goes away, or cosine becomes negative 1, sine becomes 0. So I get e to the I pi plus 1 is equal to 0, which is, of course, a very fundamental identity connecting all of the constants that we know and love. Okay, now let's actually look at Euler's identity in full through the definition. If z equals x plus iy, then the exponential e to the z is defined by the complex number. E to the z is equal to e to the x, it's the general e to the x, times e to the iy, which is equal to cosine of y plus I times sine of y. Thus we've developed a new way of writing a complex number, okay? So, now what we'd like to do is we'd like to derive Euler's identity through a fairly different way, using the Taylor series. So if you remember Taylor series, we want to look at the consistency of the Euler identity using the Taylor series and the definitions of the trigonometric functions by their Taylor series. So we want to look at the series of the exponential, and we're going to use iy as the basis, okay? So we know that e to the x is, or e to the alpha is equal to the 1 plus alpha squared over 2 factorial plus alpha cubed over 3 factorial, and etc., etc., etc. So e to the iy, we can just plug in iy for alpha. So we get 1 plus iy squared over 2, plus iy cubed over 3, plus iy to the 4th over 4, plus iy to the 5th over 5. Okay, so what we can do is we note that we can distribute the powers into the iy term, and this will give us a certain sign changes. So obviously 1 plus iy will stay the same. However, if I square I get negative 1, so I get minus y squared over 2. If I cube I get negative I, so I get minus iy cubed over 3 factorial. And then if I raise I to the 4th power, I get plus y to the 4th over 4 factorial. And then if I raise I to the 5th power, I get I again times y to the 5th over 5 factorial, etc., etc., etc. Now what we should be seeing is something very interesting. We have an alternating series, but what we want to do is we want to separate the even and odd powers, and we can actually factor out an I as well. So what we end up getting is we get 1 minus y squared over 2 factorial plus y to the 4th over 4 factorial plus ... you know what the rest is. And then I can factor out an I from the rest of the odd terms, and I get y minus y cubed over 3 factorial plus y to the 5th over 5 factorial plus ... We keep on going. Now, what we also know is that the sine Taylor series is equal to what is in this bracket. We know that the cosine Taylor series is what is equal to that in that bracket. So what we have is we have cosine of y plus I times sine of y is equal to e to the iy. There we go. We have just proved the Euler identity another way by using the Taylor series. I find this proof to be really nice, and factoring out the I and separating the even and odd powers is a subtle trick, but it is incredibly helpful, and I find it to be the most intuitive way to perform the Euler identity if you know the Taylor series for the exponential and the two elementary trig functions. So in the next video, what we want to do is we want to look at the ramifications that this has on the complex algebra that we've been developing over the past couple of units. So I would like to look at what impact it has on the argument, how we can write the complex number in complex form, and if it changes any of the properties. And of course, then we'll look at some of the examples, some more involved examples. And then finally, after that, we will consider the complex roots and powers, and we can look at the planar sets. So thanks for watching, and we will see you then.